All right, hey everybody. So today we're going to talk a little bit about how to describe and display data specifically using R and RStudio. So anytime you're working with a data set, the first thing that you want to do or that you want to think about is what's called exploratory data analysis. Basically, visualize your data, and that's what we're going to focus on today. The main things that you need to know before we move forward. First, all of the R code that I'm using to produce these graphics and these data summaries are going to use two R libraries. The first is called Tidyverse, the second is called SkimR. In RStudio Cloud, these packages will be pre-installed, ready for you to use. Just make sure you're checking to be sure that the code has run, that the libraries are in fact loaded. All of the materials that you're going to see for this class, including these slides, have actually been written within RStudio. So what you're seeing is live code exactly as it's executed. What that means is that if you upload the dataset into RStudio Cloud and run this exact code, you should get the exact same results. The other thing that I want to mention is that whenever I'm showing you guys examples in class, I'm going to make sure to use a different color palette than the default one, and we'll talk a little bit about why that is. I'll actually show you what the default color palette looks like. The palette that I'm going to be using is called CB Palette. This is a colorblind friendly set of colors. If you're familiar with hexadecimal at all, here they are. Just so you know that if your code looks a little bit different than mine and the only thing that's off in your graph is the color, this is probably why, because I'm using a custom color palette. All right, here we go. So let's start with an example. So the data set that we're going to take a look at here is called the ICU admissions data set. Now this data includes information on 20 patients that have been admitted to the intensive care unit at a hospital. We've got 16 variables in this data set, and I'm going to show you what this looks like. So first I'm using a command called read.csv. This is going to read a comma-separated file, or basically an Excel file without the formatting, directly into R. You can see the file path that I'm using to get to this file. All of the data sets that you'll work with will live in the cloud, so your file paths will look a lot shorter than mine does. But once that data set has been loaded or imported, I can take a look at the first 6 observations using a function in R called the head. That's going to show me essentially the top or the head of the data set. So here's the variables. We have a patient ID. So this is a random sample of patients admitted to ICU at this hospital. We have their status at the end of hospital admission. So either discharge, or if status is dead, the patient passed away during their stay. We have their age, sex, we have race, service, so whether they were admitted from a surgical unit or from a medical unit, history of cancer, history of renal or kidney problems, history of infection, whether or not the patient received CPR, their systolic blood pressure, their heart rate, whether they had been in the ICU previously, the type of admissions, were they in for an emergency procedure or were they at the hospital for an elective or a pre-scheduled procedure, whether or not the patient was admitted with a fracture, and then finally consciousness, were they in a coma or a stupor. So again, here are the variables in this data set listed out. One thing I want to draw your attention to in this data set is the race variable. One thing that you'll see very often in this class, especially because we're looking at information in the health sciences, is that we're concerned about identifiable data. We're concerned about being able to back solve from a data set who the patient actually is. The reason we're concerned is because this brings up a whole host of privacy issues, especially if this is publicly available data. If you're one of the patients in this data set, you might not want people to know that it's you. So when there are relatively small groups of people, as what happened in this data set, you tend to see an other category created. So this is not in any way an issue of representation or omission, as it is an issue of protecting patient privacy in this data set. All right, so let's talk a little bit about how R works. R is what's known as a functional programming language. What this means is that R is built around a set of functions that are used to tell R, hey, do this to a variable, or do this with a data set. Options within functions can be used to customize or set certain values. Sometimes we would like to save the results of these functions. Sometimes we will not. The basic syntax is this. We call a function, and then within parentheses, we give a bunch of options to tell R what the specific things we want out of that function are. This is very different from Python or Java, more object-oriented programming languages. R was designed initially for statistical computing and graphics. It has grown since then, but most of the functionality or syntax is designed around that data interaction. All right, so we're going to talk about a lot of our functions. We'll apply a lot of these, but let's start with just the basic function. Let's start with a summary function. So the summary function does exactly what it sounds like. It provides summary information for a data set. So if I call this summary function and feed in the ICU admissions data set, here's what I get, and I'll scroll down to show you the full output. For all of the variables in my data set, we get back some summary information. Depending on the variable type, it might look a little bit different. So for a numerical variable such as age, we'll get the mean or the average, we'll get the median, we'll get something called quartiles, which we'll talk about in a little bit, and minimum and maximum. For a categorical variable, such as whether or not a patient has an infection, we'll get back counts. So how many patients had an infection, how many patients did not have an infection. Let's focus in on those categorical variables for a minute. One thing we'd like to do with that categorical variables is just count up how many they are. We call this the frequency distribution. So how many observations have that category or value? Now the summary function works well to get the frequency distribution. However, oh no, sometimes we don't want all of that output from the summary function. Here's all your spoilers for later in the video. Sometimes we only want to look at infection. So instead, we might do something like this. We might take this ICU admissions data set and pipe or send it into a new function called group by. What this group by function does, again, exactly what it sounds like. It groups up ICU admissions by type, and then we'll summarize. And one summary that we might want is the number of observations, or N. So here, this tells me that 147 patients were emergency ICU patients, 153 were elective. A little bit more work than the summary function, but a much cleaner output. Let's talk about that weird thing in the middle. This is known as a pipe operator in R. Essentially, here's what the pipe operator does. It takes everything on the left-hand side and sends it through as a data set to the right-hand side. Here's kind of how this pipe works, and I apologize for not embedding this directly in the video, but this is such a cool visualization that Danielle really deserves full credit for this, so you get to see her Twitter account. Essentially, here's what the pipe does. We send Mario through a pipe. He finds his hat. There we go. We send Mario through a pipe. He still has his hat, and now he also has a flower. So we just keep sending things through and through this pipe operator and adding more as we go. That is the whole idea. That's all pipes are in a nutshell. So here's the same code that we just saw. Now, one thing that you can do in R to make the formatting a little bit easier to read, you can always hit enter after the pipe, and I'll do that fairly frequently. Hitting enter in R just continues on to the next line. As long as there is a pipe or something to add more, R will keep going. So let's take a look at this data, and maybe we want to take that 147 and we want to scale it down. We want to think about this in terms of a proportion. Like many other programming languages, R functions exactly like a calculator. So you can type any numerical calculation in R and get the answer back. So for example, if I want to know what proportion this 147 is, well, I have 200 patients. I can calculate a proportion. 73.5% of the patients in this data were emergency ICU admissions. If you prefer, you can report this in decimal form, decimals, or percents. Both are completely fine. Now, we denote this sample proportion, or the proportion in a category that we care most about, with a special symbol in statistics. We call this p hat. The p indicates that it's a proportion. The hat over it indicates that we are estimating something. So this represents our sample proportion. You'll see this symbol a lot. Now let's say we want to know how many patients in our data were 50 years old or less. Well, that's a numerical variable, but we can still come up with a sample proportion. Our new category, how many are under 50? I'm going to use a new R function here called filter. So I'm going to take the ICU admissions data set. I'm going to filter out everybody who is 50 years of age or younger, less than or equal to 50, and then summarize. How many did I observe? What's my N? Well, my N is 62. The sample proportion then would be 62 over 200, or 31%. So that's how many patients in this data set were younger than 50. As you might expect, ICU admissions skew toward the older range. All right, so that's some basic summary statistics. Let's talk a little bit about graphing in R. Now, the type of graphing package that we're going to use is something known as ggplot. The ggplot package is fairly well known in data science and statistics. A lot of the data visualizations that you see out in the wild were created using ggplot. Here's the essentials of how this works, and I should add that ggplot is part of that tidyverse library, so we get it with us for free. The basic idea, first we take a data set and we pipe it into ggplot. So we add that data set as something we're interested in working with. Anything that we want to change related to a variable gets done in one of these AES functions. AES stands for aesthetics. These are how we want the plot to look, the visual elements of the plot. These are the visual elements that are specifically related to the data. So anything that comes from a variable goes in that aesthetics. Anything else goes outside of an aesthetic. So let's make a very simple plot. We'll take ICU admissions. We'll pipe it into ggplot, and maybe I just want to make a plot of the type of admissions. What I maybe would have expected to see at this point is something like a bar chart. That's not what I get. All this ggplot does at first is establish the plotting window. So here's type on my x-axis, here's elective and emergency. Now I need to do something with that. The way we do that in ggplot is with what are called geometries. So geometries are the shapes of the plot, what we're adding to it. Geom_bar indicates that we want to add the bar geometry. We want to add a bar chart layer to our plot. We do this using the plus sign. So anything that we are adding to a plot comes after a plus. So here's elective versus emergency. There are a lot of things we could do to jazz this plot up. One might be to set the bars to be a different color. Here's how I can do that. The fill of the bar is what's dictating the color. So I might change the fill or the shading of the bar to depend on the plot type. So elective is one color, emergency is another. I can also add labels using this labs command. So my X label is now admission type, My Y label is number of patients. And then I've added one more thing. I've added a manual set of colors using that colorblind palette that I told you all about at the very beginning. So we've got orange for elective, blue for emergency. If I don't add that colorblind palette, I end up with the default color palette in R, which if you like coral and teal, is pretty good. However, it's not the most accessible pairing of colors. It can be difficult for some people to see. If you like these colors, awesome. You can stick with these. As you add more colors or as you add more categories, the color range breaks up farther and farther. As you can see, when you get to 7 or 8 colors, it becomes a lot more difficult to discern each of these categories from one another. The good news is we have plenty of customization options for our plots, and I'll show you guys some in the next few slides. So that's categorical variables, or the very basics of categorical variables. Let's move on to numerical variables. So for example, how do we describe the age distribution for ICU patients? Well, one nice geometry for numerical variables is a histogram. Histograms are just like bar charts, but we build them for numerical variables. So the height of the bar tells me how many categories are within a specific age range. So looking at this, I can see that most patients are between age 50, which is right here, and 75. It looks like there's a peak somewhere between about 60 and 75. So this peak looks like maybe it's at 65 to 68. And then below 25, there's another peak in the data. Again, here's how those histograms work. So we take the range of our numerical variable and we split it into what are called bins of equal width. So if we go back to the previous slide, here I've set bins equal to 20. If I count how many of these bars there are, how many of these bins there are, there should be 20. So each age has been broken into one of 20 different categories. We count up how many observations fall into each bin, and then we draw a bar for each bin where the height corresponds to the number of observations. So again, here is our same histogram. If we make some changes, if we change these bins, we'll affect or we'll change the width of the variables ever so slightly. And in fact, we can head over to RStudio and give that a try. So here's the code that was used to create those slides. We'll scroll to histograms. Here's the code. If I change this to 20, run everything previously. It's always a good idea when you're jumping into a code document to run everything that came before. We'll hit the play button, and you can see that the bins are now slightly different. If I change the bins to a larger number, the resolution will become even finer. So we have the option to sort of adjust this plotting choice. Now, when we're looking at these histograms, here's the things that we try to look for. We try to look for the middle. What's the center of the distribution, or the typical value of the distribution? We also look for the shapes. So there are a couple shapes that are commonly observed that tend to repeat in real data. We also look for how spread out the distribution is and whether there are any unusual observations. So for example, here are some common shapes. So one thing that you might see in real data is a bimodal histogram. We have a large concentration of data here. We have a large concentration of data here. So if we've got two major peaks, the histogram is bimodal. Whereas if you look at the second histogram here in the upper right, this example is unimodal. There's one major peak. This example is also what we would call skewed right. Notice how there's a big peak in the data here, and then everything kind of trails off to the right side of the data. Data that's skewed left would have the exact opposite shape. There would be a peak on the right side of the histogram and a tail to the left. Think of the skewness direction like how you would be stretching or pulling the data. whatever side you're stretching it from is the side that is skewed. On the bottom left, you see an example of symmetric data. So here we've got roughly the same pattern on both sides of the scatter plot. And then finally, this bottom left one, or sorry, bottom right one, this yellowish one, there's really not much going on. There's kind of a peak here. You have to squint at it. If you can't see any major pattern, or if it's fairly flat overall, we refer to this as uniform. So pretty flat, pretty boring. One of the other things that we look for are outliers. So these are observations that are pretty far beyond the range of other values for that variable. These can be really small values or really, really large values. Now, your textbook has different rules of thumb or tests even for identifying outliers. I like to rely on just the visual test. You'll know outliers if you see them. So, for example, if we take a look at the histogram of heart rate in this data set, I would call it fairly unimodal. We have kind of a nice curve here. There's a peak of heart rate somewhere between 75 and 100. However, we have one patient over here with a very high heart rate, near 200. So this patient might be an outlier. One thing to notice here is that I've changed the color of this histogram from the default sort of dark gray to blue. And I can do that just by typing the word blue in quotes, and R will know that I want blue. All right, so let's talk about another graph for another data visualization for numeric data. Let's talk about box plots. Like histograms, you may have seen these before, but maybe not gone through all of the parts of a box plot. So here's what a box plot looks like, and here's the basic breakdown of what you're looking for within that box plot. The thick dark line inside the box, so kind of in the middle of the box, that represents the median or the middle 50% of the data. The outside of the box represents what are called quartiles, and these quartiles are cutoffs for the lower and upper 25% of the data. So looking at emergency patients, for example, 25% of them are below age about 35 and younger. 25% of them are about 70 and older. 50% are in this blue shaded range here. If there are any outliers in this, you'll see them identified with a dot. So for example, there are 2 patients who were admitted for elective procedures that are much younger than the rest, that are deemed outliers. The plot geometry to create these is geom box plot. So all I've really done here is just added a box plot instead of a histogram. Notice type is on my x-axis, age is on my y-axis. So that's how I built or constructed this plot. The next plot for numerical variables that I want to look at is a scatter plot. And these are plots that you know and love, but we'll just go through some basic terminology for these. So take a moment. Do you think there's a relationship between a patient's age and their heart rate? Let's find out. So, looking at this scatter plot, pretty obviously no. The points are literally scattered just about as far as you can get. Here's how this plot was generated. So my x variable is heart rate. My y variable is age. So I have heart rate on the x-axis, age on the y-axis. The point geometry in R says to just simply draw points at those observations, so create a scatter plot. And then my labels, x is patient heart rate, y is patient age. Now, if you don't include these labels, what R will do is write the variable name in the label space. So this will say heart rate without a space. This will say age. It's a good idea as you get more and more comfortable working with R to go ahead and add those labels to your plots just to make them look cleaner and more professional. All right, so if we have any 2 variables that are related, in statistics, we refer to them as associated. We don't always call them correlated, but we sometimes do. Correlation has a very special meaning. It describes a certain type of association. So for now, any two variables that are related might be associated. So one example could potentially be systolic blood pressure and heart rate. The points are clearly a bit closer together than they were before, but still, there's not a lot of trend in this scatter plot. So there's really no association between heart rate and systolic blood pressure. If we did have an association, though, we might see something more like this. So this is an example of a scatter plot that's showing positive association. Essentially, we have an upward trend. As the x-axis variable is increasing, or as x is increasing, y also tends to increase. It might not be as clear as this is, but this shows that there's a clear relationship between the two variables. If we have a downward trend in statistics, we refer to that as a negative association. And this is a pretty strong negative association. As x is increasing, y is clearly decreasing. All right, so let's talk a little bit about looking for association in real data and some techniques that we can use to help us accomplish this. So one thing that we can do is break up our data into smaller groups and maybe find some associations within subgroups of our data collections. So I'll show you two side-by-side scatter plots here. The code that you're going to look for, or the things that I'm going to use to help me out here. First, this facet wrap, that's going to be what I use to split my data up into those two plots. Geom smooth, that's going to add a linear trend line or a linear model. That's where method equals LM comes from. On your first RStudio Cloud project, which you'll complete after watching this video, you'll get to see what happens when you take away some of these options and how that changes the plot. So here's what we're looking at. On the left-hand side of this data, we have the elective admission patients. On the right-hand side, we have the emergency patients. There's still no clear trend. However, I've added sort of a linear trend line to each of these. There's maybe a slight upward trend for the elective group, maybe a slight downward trend for the emergency group. The trend is not strong in either case. Now, let's talk about calculating some summary statistics in detail. So summary statistics are just numbers that are providing some information about certain features in a data set. Two that you're probably familiar with are the sample mean and the sample median. So the sample mean is the average of all individual observations in the sample. So the formula for calculating the mean, we add up all of the individual observations and divide by the sample size. Throughout the semester, we'll use n to represent the sample size. The sample mean gets denoted with an x bar. So x for my variable, the bar over it indicates that it's a special type of statistic, specifically an average. The sample median is just the middle observation. So we group or sort observations from smallest to largest, find the one in the middle, and we'll use an M to denote that. So here's a couple ways that we can find the mean and median age. So the first thing that I can do is take this ICU admissions data set, pipe or send it into a function called summarize, and I can calculate two summary statistics. Mean is the mean of the age variable, median is the median of the age variable. If I want, I can add an extra step here. I can group it up by type first. So then that's going to calculate the mean and median for each of these admissions types. So we can see that patients who are admitted based on an elective procedure or following an elective procedure tend to be older. The mean age is about 64 compared to 55 for the emergency patients. Median's about 68 compared to 60. So there are some differences between those patient profiles. I can make this a little bit more complex, so I can find the range and the quartiles. The range is the difference between the minimum and the maximum. So the range would be 92 minus 16. The quartiles, these are also known as quantiles. So we'll take the 25th quantile, the 75th quantile, If this seems like a lot of code to get this table, you're right. There's a much easier way to do it. So in that skim-r library, that's the other library that I told you about at the very beginning, there's a function called skim. So we'll take the ICU admissions data set, we'll select our age variable, and then we'll just skim it. We'll see what this age variable looks like. So this tells me what the variable type is. These are integer values. There are no missing observations. There are 200 complete observations. The mean is 57.5. P0 is the minimum. P100 is the maximum. P50 is the median. P25 and P75 are the quartiles. We also get kind of a nice rough histogram of the data. One statistic that I skipped over is SD, and let's talk a little bit about what this SD represents. SD stands for standard deviation. So standard deviation is a measure of how spread out a data set is. It tells us the typical distance between an individual observation and the sample mean. So large standard deviations indicate that observations are spread out from the mean. Smaller standard deviations indicate that they're a lot more concentrated, that they're narrower. Here's the formula for standard deviation. Like I said at the very beginning of class, this is one of those things that I never calculate by hand, so I wouldn't expect you guys to do that as well. One thing that's kind of weird about this variable, or this formula, excuse me, is that standard deviation is not actually an average. So to calculate standard deviation, we take the difference between each individual observation and the mean, we square it, add those all up, divide by n minus 1. Then we take the square root to undo, essentially, that square. But we're not averaging those deviations. We're not doing that. The reason that we divide by n minus 1 is because we get a better estimate, or an unbiased estimate, of the population standard deviation, sigma. So it's a little weird that the standard deviation doesn't represent the average distance or the average squared distance. It's because we get a better estimate of how varied the population actually is when we divide it this way. Now, the standard deviation is the square root of something else in statistics known as the variance. You might see this term variance pop up throughout the semester in some R output. What you need to know about variance is that it has really nice mathematical properties, but since that variance is the standard deviation squared, it's not on the same scale as the original observations are, whereas the standard deviation is. Where the variance is a lot more useful is in probability theory. So if you're interested in math or stats or data science and end up taking more courses, you'll see variance come back up. All right, so standard deviation has a really great interpretation. What it represents is the typical distance between an observation and the mean. So it tells us about how far apart most of the observations actually are. So if we want to see something about how varied the ages of ICU patients are at this hospital, well, here's one thing that we could say. We could say that the typical ICU patient, or most ICU patients at this hospital, are going to be somewhere between 37.5 years old, that's just the mean minus the standard deviation, and 77.6 years old, or the mean plus a standard deviation. So that gives us a really nice and quick rule of thumb range for how wide the data is, or a rough idea of where most of the observations fall. If we break this up or group this by type, we can see that there are some differences. Elective is the top row, emergency is the bottom row. So here's our rough histogram for the age of elective patients. Here's our rough histogram for the age of emergency patients. Clearly, the emergency patients are a lot more spread out, and they have a higher standard deviation. So the age of emergency patients tends to be more variable. We can see that through the histogram, but we can also see that through the standard deviations. And here's that same data in a slightly different representation using a ggplot histogram. We can still see that there's quite a bit more variation in the emergency patients compared to the elective patients. Now, one thing that I like to remind students of at this point, summary statistics don't tell us everything. They don't tell us about the individual observations. They don't tell us what the details are. They're really just aggregations of what's underneath. So those summary statistics like standard deviation really should always be accompanied with a visual. What do the individual observations look like? What does the data look like? All right, so let's move on to categorical variables, and we'll talk a little bit about how to compare categorical variables. One common data representation that you see in research papers or journal articles or clinical reports is a contingency table. These are frequency tables with 2 or more categorical variables. So that group by function, we can add more to it. We can group by multiple variables. Here, I'm grouping the ICU admissions data set up by cancer and type. So the summary table that's produced has 3 columns. We have a column for whether or not the patient has cancer, yes or no. Column for whether or not the patient is elective versus emergency, yes or no, and then the number. One thing that I should mention here is that this FCT in pointy brackets stands for factor. That's how R refers to categorical data. The INT refers to integer. Contingency tables usually, though, look like this. Most of the time you would see them with one variable on the rows, one other variable on the columns. So cancer, admission type. Good news, we can reformat our variable directly in R, so we don't have to copy all of those numbers up one by one. We can do that by using a spread option. So what the spread option does is take this table that I created previously and spread it out. So we're going to spread it out by type. So now here is type, elective, type, emergency, and it's spread out my table just a little bit. There is an easier way to create a table like this that we'll see pretty soon, but this is a good visualization as well. Again, the table doesn't tell us the whole story. We like visuals, so let's take a look at this data. One option is to create a stacked bar chart to compare these 2 categorical variables. So the x-axis has cancer, so patients without cancer, patients with cancer. The fill, or the colors of the bars, is indicated by the type of the admissions. So blue is emergency, orange is elective. This does a really good job of telling the story about the relationships. So for the for the no cancer patients here on the left, the majority of them came in the ICU after emergency procedures. Only a few were elective. Whereas cancer patients were much more likely to be coming to the hospital for pre-scheduled elective procedures, which makes sense because patients with a history of cancer are more likely to be receiving regular treatments. We can modify this a little bit more, so maybe we don't like that stacked appearance. Maybe we want to use faceting. Faceting, again, splits the graph into multiples. So here we have a bar chart for elective, bar chart for emergency. Notice that the fill is still set to type, so we're still changing that color shading. Or we can use a dodge, bless me, we can use a dodge position to, instead of stacking those bars, split them apart. So dodge them or make them dodge each other. Same sort of idea. For the cancer patients, they're more likely to come in after an elective procedure. Non-cancer patients are more likely to come in after an emergency procedure. All 3 of these graphs are equally valid and tell the same story. It's just a matter of which representation you like the best. All right, so what are the takeaway points here? So as you're kind of gathering, we have tons of options for graphing, exploring data in RStudio. We haven't even scratched the surface in this video of what is available for us. The good news is we'll practice a lot and you'll get tons of sample code to use working forward. So we've got a few more visualizations here in the slides, and your handout should have the code to produce each of these. What I would recommend is going through each of these visualizations, trying to write an interpretation and see if you can think through how this code is going to be created. So for example, does sex affect the relationship between heart rate and systolic blood pressure? Looking at this plot, I know that my x-axis is heart rate. My y is systolic blood pressure. It looks like I'm faceting by sex or gender, and I'm also changing my plot color by sex or gender. So there should be a color equals sex command here. Does sex affect the relationship between type of admission and probable infection status? Here it looks like we have admission type on the x-axis. We've got a fill or a shading argument for the infection type, and then we're faceting male and female. Here we've got a scatter plot of heart rate against systolic blood pressure. We're then faceting this by race, changing the plotting color. Again, here you can see that issue of identifiability creeping in. Out of all of the patients in this data set, the vast majority were white, so this is reflecting the area in which the hospital was originally located. Some were black. There were very few patients in this data set that represented other minorities, so to protect their individual privacy, they are all grouped into that other category. And then finally, taking a look at a scatter plot of patients admitted to the ICU, age compared to history of renal failure, we can see that patients with history of renal failure or kidney problems tend to be older, probably a higher mean, probably a smaller standard deviation for this yes group as well. That is it for section 3, displaying and describing data. Now's a good time to get started on your first RStudio Cloud project. I'll see you during our next class meeting on Tuesday, January 30th. Have a great day.